Hello everyone, welcome to the Geoecologist. I'm Dr. Krishnanand, and in this session on physical geography, we are going to learn about the concept of the internal structure or the interior structure of the Earth. So before we go ahead learning about the external structure, about the mountain, plateaus, plains, valleys and other features of the surface of the Earth, it's also important at the same time to learn about the different materials, the processes that are happening beneath the surface of the Earth. So in this session, we are going to talk about the internal structure. But before we go ahead, please like and subscribe to our channel and don't forget to press the bell icon for the updates. So let's understand about the internal structure of the Earth. So what is beneath the surface of the Earth? So when we talk about geomorphology, it basically talks about the surface feature of the Earth. But before knowing the surface feature of the Earth, we must understand about the interior of the Earth, what is the structure in the internal portion of the Earth, and what kind of material is there, what kind of process is there. So all these information is important in order to understand that what is happening at the surface of the Earth. So what are the basic questions? The first question is, why do we need to know it? The second question is, how do we know about it? And the third question is, what do we know about the internal structure of the Earth? So let's understand. So in order to know about the internal structure of the Earth, we must understand that what are the sources? How do we get the information? So there are two kinds of sources. One is known as the direct source and the other is called indirect source. So let's understand what is a direct source. So direct source include rocks from mining area. Apart from that, the volcanic eruptions. So these are two important direct sources. So we can study the rocks in a mining area and understand about how those rocks must have formed, about the cooling of the Earth millions of years ago and how gradually these rocks come up to the surface. Then volcanic eruptions. As we know that during a volcanic eruption, the material from the inside comes to the surface. So this material brings lots of information. So that is why it is called direct sources. Now let's learn about the indirect sources. So when we talk about indirect sources, the first important thing is rate of change of temperature and pressure. So this is an important source of information that we get from the rate of change of temperature and pressure studies. Then meteors. Why meteors? Because we have already studied about the origin of universe, about the solar system and the Earth. So meteors or the other celestial bodies are part of the same universe. So we say that when we study meteors, it can also give us information about the primordial matter of which the Earth is made. So that is why it becomes important. Then gravitational studies. So the gravitational anomalies across the latitudes, right from equator to the pole. So that is another indirect source. Apart from that, gravitational anomalies. So there is a change of gravity effect because of the mass of the material, the quality of the material of which it is made. So that is what another important source is. Then we have magnetic surveys that provide information about the distribution of these magnetic materials. Then what we have is the seismic waves, that is the primary and secondary wave. So let's understand few facts. So average Earth radius is 6371 kilometers. Equatorial radius of the Earth is 6378, while at the polar area the radius is 6357. So what we observe is it is the lowest at the pole, alright, and highest at the equator. So why is it so? While average is in between that pole and equator, that we say 6371. So why is it so? We'll learn. But before that, what is the meridional circumference? It is about 40,008 kilometers. But now let's answer why is this so? This is because of the shape of the Earth that we say. So Earth's shape is like oblate spheroid that we say. It basically means that it is bulged out at the center and it is flat at the poles. So what happens? The distance which is here and the distance which is here both have differences from the center of the Earth. So that is why it is different. So average value is 6371 while the equatorial radius is 6378 and polar radius is 6357. So remember these figures. Now let's talk about the pressure and temperature gradients. So what does this have to say about the interior of the Earth? why these changes are there. So pressure and temperature both in general way increases with depth. So as we go inside the earth from the surface, we find that both the things, pressure and temperature, increases. But remember, it's not in a regular manner, it is in a irregular manner. The fact that temperature of the earth increases with increasing depth below the surface was first clearly enunciated in 1966 by the scientist Kircher. So Kircher, first time in 1966, when he was studying the interior structure, he talked about that the temperature is actually increasing if we go deep inside the earth. So this was first thing, and he obtained this data from the mining activities in Hungary. So that is important. So what we find is, on an average, the temperature increases by about 25 degrees C for every kilometer of depth. But this is an average value. It means it can be above, it can be below this value across the surface of the earth. So average value is 25 degrees C. So what we see here is, in tectonically active areas, 1000 degrees C at 43 kilometers. This is the temperature. At about 2900 kilometer in the depth of the earth, it is about 3700 degrees C, and at 5100 kilometer, it is about 4300 degrees C. So that is the important thing we need to understand. And apart from that, if you look into this image, you find the total interior heat flow. So crust has 24% of that, upper mantle has 22%, lower mantle has 32%, and core, including outer and inner, has 22% of the total interior heat. So the heat that is there inside the earth has this kind of distribution, which may be asked in a multiple choice question. Furthermore, let's observe these two images as well. So this is talking about the temperature gradient that we see here. As we move further ahead, we find there is an increase in temperature as we observe. Similarly, looking at this particular image, we find that there is also increase in the pressure as we go to the center of the earth. Apart from these important trends that we study, it's also important to understand the SI unit. Okay, so what is the international unit for measurement? So that is called Pascal. It is for basically pressure. So 1 Pascal is defined as 1 Newton per square meter. A pressure of 1 Pascal is small. Therefore, everyday pressure are often stated in kilopascal. Alright, so 1 kilopascal is about 1000 pascals. That is important in terms of pressure. On temperature basis, now we see 0 on the Celsius scale is basically what? In terms of Kelvin, it is 273.15 Kelvin. So if you observe here the temperatures in Kelvin, you can convert it into degrees Celsius. Apart from that, there is something called standard atmospheric pressure. So that is also called ATM. Alright, it's not that ATM from where we withdraw the money. So this ATM is basically standard atmospheric pressure. This is basically 101.3 kilopascals. So this is standard, which is everywhere on the earth. So some kind of standardized value and an average value. So this is about 101.3 kilopascals. So if you see somewhere this unit kPa, or maybe what you see here is GPa, that is giga. So as we understand, kilo, mega, giga, all these things. So these are the units. So this is talking about the pressure that keeps on increasing as we go in the depth. Apart from that, atmospheric pressure at sea level is also measured in pounds per square inch. So that is called PSI. So that PSI value is 14.7. So these are certain important facts and figures that we need to understand when we are talking about the pressure and the temperature also beneath the surface of the earth. Now, when we talk about the indirect sources, the most important indirect sources are these waves, and these waves are the seismic waves that are propagated due to the internal disturbances inside the earth. So this wave factor gives us lots of information as they travel through different mediums, through different layers of the internal earth. So one is called primary wave, that we know by the name of also P wave, and the other is called secondary wave. So that is important as S wave. So let's understand some of their characteristics here. So P wave travels through liquids and solids both. It pushes and pulls material as they move through the earth. That is important. It travels about 8 km per second. So that is its top speed. That is important here. Now, it causes the first movement you feel in an earthquake. So it is about the first wave that comes from the interior of the earth that hits the surface of the earth. So that is related to the earthquake that we see. Then secondary wave travels through solids. That is important. It does not travel through liquids. Also remember, it travels through molten state, but it has to be 90-10 ratio. It basically means that it should be at least 90% solid and 10% molten only. Then only secondary wave is going to travel. That is important. Now, it makes the rocks vibrate up and down or sideways. Basically, if this is the line of propagation, so the material perpendicular to this also is moved by this wave. So this is why this wave is also known as transverse wave. Alright, so it travels about 4.5 kilometers per second. So there is a difference in speed. As you see, it is 8 kilometer, it is 4.5 kilometer, and it usually causes more building damage. It is the second after the primary wave to reach, and because there is a sideways movement as well, it is transverse in nature, as we know. So that is important to understand here. Now, both of them originate from the same focus. They begin at the same time and can be felt at Earth's surface. So that is the commonality. So that is important here to understand the characteristic of these waves. And if we want to understand the interior structure of the Earth, about the characteristic of the different materials in different layers, we can understand it through the studies of these waves. Now, another important concept that is related to this seismic wave is the shadow zone concept. So for P wave and S wave, let's observe these images and understand how these shadow zones are there and why these shadow zones are there. So as we remember, P wave can travel through both liquid and solid state, but S wave cannot do the same. So what happens? There are certain mediums inside the Earth interior where the situation is not favorable for S wave because it is in liquid form. So what happens? It deviates from there. It does not cross through. So that is why that particular zone which it does not cross through is called shadow zone, because that wave cannot travel. So if you look into these images, look here, degree 103 from this point to this point. So this is about 154 degrees. This is what the shadow zone looks like for the S wave. Why? Because remember, the outer core is in liquid state. So S wave originating from the epicenter, if you observe here, it cannot move inside this particular outer core. So this particular zone, right from 103 to 103 this side, right? So this zone is actually shadow zone for S wave. While for P wave, what we observe? For P wave, we also have certain shadow zones. For example, the angle between 103 to 150 largely, but many places you'll find 142 or 144 as well written. So don't get confused. This is basically an average value that is being taken. So roughly you can understand from 103 or 104 degrees to 150 degrees, this zone is where P wave is also absent because of the deflection factor. So this is for P waves, but P waves can pass through the core as well, but S wave cannot pass through the outer core. So you can find different images and you can study the same, but remember the concept of this shadow zone in relation to the characteristic of these waves. Then you can understand it more clearly. Now, one by one, let's understand the different layers of the Earth. So first layer is the crustal part of the Earth. So what we observe here, the thickness of the crust varies in the range that is 5 to 30 kilometers in different parts of the world, and especially where oceanic crust. While in terms of continental crust, it varies where between somewhere around 50 to 70 kilometers. So somewhere you will find 65 kilometers written, somewhere 60 kilometers written, but this is in between this range, so 50 to 70, and this is the oceanic crust which is in 5 to 30. So remember, oceanic crust is thinner and continental crust is thicker. So many times this question can be asked in multiple choice question. Now, continental crust can be thicker than 70 kilometer in areas of major mountain systems. For example, if you see Himalayan region, it has about 70 to 100 kilometer thick. That is important here. Now, in terms of volume and mass, remember this fact that it is 1% of the Earth's volume and 0.5% of Earth's mass that is there in the crust part. Now, constituent elements of the crust are largely silica, that is Si in terms of its symbol, and aluminium, that is Al in the symbol. So what we say is it is Cr. So according to the scientist Suez, he classified Earth's structure into Cial, Sima and Nephe. So that is the old classification that we study. So this Cial is basically the crustal layer where you have silicon and aluminium. So silica and aluminium is the top component. And here density increases with depth. Now remember this particular line, that in crust what happens, the density increases with as we go in the depth. And average density is about 2.7 gram per cubic centimeter. So this is a fact to remember. And average density of the entire earth is 5.5 gram per cubic centimeter. Now let's observe certain more facts and figures related to Earth's crust and also the entire Earth comparison. So if you observe, what we see here is that maximum component, that is the maximum occupancy is of oxygen in the crust, that is about 47%, then silicon, that is 28%, then what we have is aluminium, which is 8%, iron is 5%, magnesium is 4%, calcium is 2%, potassium is 2%, sodium is 2%, and others are 2%. So what we see is the maximum component, which is oxygen. So if you want to remember, you can take a shortcut as well. So what you can do is remember like this particular short form. So you can make a simple short form like this. So OSAIMCPS. So if you want to create some word related to this, you can do it yourself, which you can remember easily in terms of the descending order or maybe ascending order. So maximum presence is of what you see here is oxygen, and then in the crust we have what is silicon and then aluminium and iron. It changes when we talk about the entire earth, not just the crust. So what is that change? Look, this iron, which is only 5% in the crust, now goes to the top. So in the entire earth, maximum content is the iron, that is 35%. Then it is oxygen, which is 30%, and then it is silicon. Alright, so that is important. You can remember by this iOS, like software. So iOS is important. So IOSM you can say, or NSCAO. So again, you can make your own shortcuts of this to remember it in an easy way. Let's look at the other layer, that is called asthenosphere. So what is it? It is 80 to 200 kilometer deep layer just after the crustal layer that we say beneath the lithosphere. So it is viscous, mechanically weak and ductile, deforming region in the upper mantle part. So now remember, it is also known as low velocity zone. Why so? Whose velocity? The seismic waves velocity. Why? Because it is viscous in nature, it is mechanically weak and ductile. So what happens? The P wave and S wave that travel through this layer becomes slow in this zone. That's why it is called low velocity zone. And remember, for our plate tectonics, the plate movement, this layer is an important layer because our lithosphere plate move or glide on this particular layer, which we say asthenosphere. So that is important. Now, what is mesosphere or pyrosphere? These are two other terminologies that we should remember. So region below the asthenosphere. Alright. So as we remember, asthenosphere is part of the upper mantle, just beneath the crust. So what is this mesosphere or pyrosphere? It is the region below asthenosphere but above the core. So basically that is entire mantle part leaving this particular asthenosphere part of the upper mantle. Now let's learn some things about mantle. So it is the interior beyond the crust that we know by the name of mantle. Its thickness is about 2900 kilometers and the major rock type that is there in the mantle is peridotites. Alright. So peridotite is what? It is the dominant rock of the upper part of the Earth's mantle. The composition of peridotite nodules found in certain basalt and diamond pipes, that is kimberlite. Remember the diamond pipes, the diamond ores from where we receive diamond. Kimberlite comes out through many times mining activity or volcanic activity as well. So are of some special interest because they provide samples of Earth's mantle, and that's where we learn about the mantle, that how is it there, what is its characteristic. So it constitutes of basically 84% of Earth's volume. So remember, this is the major chunk of the Earth. So mantle is 84% of the Earth's volume and 67% of the Earth's mass. So this is the two important thing to remember here. It constitutes of basically these elements: 45% oxygen, 21% silicon and 23% magnesium. So you can remember by this OSM. So OSM is the key: oxygen, silicon, magnesium. 45, 21, 23. The density of upper mantle varies between 2.9 to 3.3. So this is a range. Remember, 2.9 to 3.3 gram per cubic centimeter, while the density of lower mantle, where the hardness is more, so what happens there? It is 3.3 to 5.7. So if you look at this range in an entire way, it is 2.9 to 5.7. But there is a break in upper and mantle because of the change of the material. So upper mantle has little molten state or little of diffused state of matter. So this is important to remember, that its density is lesser, while lower mantle is harder, so its density is more. Now let's learn about the core characteristics. So core is divided into two parts that we know by the name of inner core and outer core, and associated are the scientists' name who discovered about these. So the entire core, when it was not divided, the core was thought of a singular sphere. It was considered as a single part of the internal structure of the Earth. It was given by D. Oldham. So he studied this particular earthquake record, and in 1906 he talked about the concept of the core of the Earth. But in 1929, Danish seismologist Lehmann, he talked about the division between inner core and outer core. So that's how this concept emerged in the early 20th century. So inner core is in solid state. Remember, inner core is solid, outer core is liquid. Okay, and apart from that, there is another terminology that we should remember, that is barysphere. So this term barysphere is basically referring to the core of the Earth, or sometimes the whole interior of the Earth as well in terms of the core. It's not divided into inner or outer core. It's talking about the entire core. So that is also known as barysphere. So now let's learn about certain characteristics of this outer core. So outer core surrounding the inner core lies between 2900 to 5100 km. So that's important. After that, outer core is composed of iron mixed with nickel. That's why it is called Nephe layer, remember, and trace amounts of lighter elements. So in a very insignificant amount, lighter elements are also there. But majority is this heavier elements, that is nickel, alright, and ferrous. So that is why it is called Nephe. And outer core is not under enough pressure to be solid. That's why it is in liquid state. So this we'll also be discussing later on. The density of outer core ranges from 9.9 to 12.2. Now remember, outer core range is this particular range. So 9.9 to 12.2 gram per cubic centimeter. The temperature of outer core ranges from 4400 degrees C to 6000 degrees C in inner core. And remember, this dynamo theory suggests that convection in the outer core combined with Coriolis effect gives rise to Earth's magnetic field. So according to this dynamo theory. So that is important, that because there is a liquid core hypothesis on which we say that Earth's magnetic field is created according to the dynamo theory. And now talking about the inner core. So inner core extends from the center of the Earth to the 5100 kilometer mark. That's where the division is between the inner core and outer core. And inner core is generally believed to be composed primarily of 80% iron and some other parts, that is nickel and ferrous combined. So since this layer can transmit shear waves, that we say transverse seismic waves, remember transverse waves. So when P waves strike the outer core, inner core boundary, they give rise to S waves. So when P waves attack this particular segment where we have this inner core and outer core boundary, that is where S wave is also generated. So that is important. This solid inner core is too hot to hold a permanent magnetic field. So solid inner core does not have a permanent magnetic field. It is morely about outer core, which is in liquid state. So dynamo theory, as we talked. So density of inner core, now it is 12.6 to 13. So this is what is important. Some places you will also find written 14.3 or something. So that may be a change in the values, but general standard value is 12.6 to 13 gram per cubic centimeter regarding the density. The core, that is inner and outer core, accounts for just about 16% of Earth's volume, but 33% of Earth's mass. So that is important. Now, scientists have determined that temperature near the Earth's center to be about 6000 degrees C, that is 1000 degrees C hotter than the previously thought in terms of the earlier theories. So it's somewhere close to 6000 degrees C in the inner core. Now, what is important here is a thing called discontinuity. What is this discontinuity all about? This is about the discontinuity between these various layers, the transition part that we observe, that one layer is different from the other layer. So how do we know this? By studying these discontinuities. So what are these discontinuities? First one is the Conrad discontinuity. So it is between the oceanic and the continental crust. That is the first one. Then what we have is between the lithosphere and the asthenosphere, that is Moho discontinuity. Then what we have is the next one, that is upper mantle, and the lower mantle, that we say is Repetti discontinuity. And then between lower mantle and outer core, it is Gutenberg discontinuity. And finally the outer core and inner core, remember the name of the scientist? Lehman. So he discovered it and said that outer core is different from inner core, that is called Lehman discontinuity. One example is that Moho discontinuity, that is this particular discontinuity is because of this change in the rocks. Similarly, other layers are also there only because of the change in the composition of rock. So one example is the feldspar. So what we see, the rocks containing feldspar are above to the rocks containing no feldspar, and that is where this change is observed, and during Yugoslavian earthquake, this Moho discontinuity was discovered around 1940s. So as we know that there is enormous temperature in this region, there is also enormous pressure. So that raises the melting point of iron and nickel. So this is basically what we say is the melting point of Nephi. It is raised. So what happens here? As we move out from the solid inner core. So remember, inner core is more dense and it has more temperature. But as we move out and we go to the outer layer, what happens? The temperature drops and the pressure also drops. So majorly because of this pressure change, it is in the liquid form. There is not enough pressure in this belt to actually hold it into the solid state. So that is important here. And at last, let's take one question. So consider the following statements in context to the structure of the Earth. So first statement is lower portion of the mantle is called asthenosphere. Second is inner core is in liquid state and outer core is in solid state. Third is oceanic crust is thinner as compared to the continental crust, and these are your options. So just think about it and what is the correct option? It is saying find out the incorrect one. So which of the above statements are incorrect? So remember, when we solve any of these MCQs, remember what is exactly is asking. So what is the answer here? It's C. And what is the C option? 1 and 2. Remember, statement 1 and 2, these are basically incorrect. Why it is incorrect? Remember, lower portion of the mantle is called asthenosphere. No, it is the upper portion, right? And what happens? Inner core is in liquid state. No, what is in liquid state? Outer core is in liquid state. So that is where the catch was. Alright, so you can practice similarly more questions based on the concepts of interior or internal structure of the Earth. So now, when we have learnt about the internal structure of the Earth in details, remember all those facts and figures related to the density, the material, the P and S wave, and all these concepts that we study are important. So I hope you learnt well. So all my best wishes. Stay safe, stay tuned, take care.